Hello everyone, welcome to my organic chemistry mini lecture. Today we will talk about the 3D structures of organic compounds. Um, First, let's talk about what's the perspective structure. I use methane as the example. So this shows the methane's perspective structure. Um, I use a different color to show the four hydrogen. They are actually the same atoms. I just want to use the color to tell the position or orientation in this perspective structure. This kind of structure is called tetrahedral. Um, so if you see this just normal single line, that means the bond is in the plane. This is also in the plane. And if you see the wedge, and that means out of plane, and it's pointed to you, closer to you. And if you see dash, and that is out of the plane and it's away from you. Okay. And if you look at this structure from left, you will see this structure. So this still the vertical hydrogen, but you will see this red hydrogen pointed to you if you look from left, point to you and to your left. And the green hydrogen will also be pointed to you and but will be your right. This blue hydrogen from left view actually will be away from you. Okay, so now if you look at this tetrahedral from right side, and then you actually will see, again, this vertical is the same, but this blue hydrogen will be pointed to you, and the green will be away from you to your left. The red will be away from you, again, to your right. Okay, this is right view. If you look from top, then this hydrogen will be closest to you. This is this one small. I use a small purple ball shows this hydrogen, and I use the purple, dark purple. Okay, sorry, pink ball as the hydrogen, and the dark purple ball it shows carbon here. Since carbon is bigger than hydrogen, so you should be able to see the carbon. And then the other three hydrogens, the red, green, the blue, they are all away from you if you look from top. And the red will be point up away from you, green will be pointed down away from you, and blue will be your right. They are all away from you. Only this hydrogen, the pink hydrogen, will be pointed to you. But you will not be able to see the bond. Okay, it will be blocked by this hydrogen atom, the pink hydrogen. If you look from bottom, you will see the carbon, the dark purple here, and that's this carbon. And you will see the green hydrogen point up but pointed to you. And red will be down and pointed to you. The blue will be right, also point to you. The pink hydrogen will be blocked by this carbon, so you will not be able to see it. And this is the tetrahedral. The real 3D model will be shown here. So that is the tetrahedral. And this carbon is sp3 hybridized. Okay, now let's look at the other type of 3D structure. It's called Newman. The Newman projection of organic compounds shows the conformation along the two carbons. So if you look at, along two carbon, this is the one carbon, this is a dot in front, so it's a front carbon, and you will see a circle that is the carbon behind it. Okay, this shows the substitution on these two different carbons relative position. So like this is called anti. You see this methyl group is the largest compared with hydrogen and the bromine, the three attachment on the same carbon. This methyl is biggest. Then the other carbons, three attachment, hydrogen, hydroxyl group, and the methyl group. Methyl is also largest. So these two largest group on these two adjacent carbons are opposite. So one is up, one is down. So they have minimized, they have basically no steric hindrance or steric interaction. So that conformation is most stable is called anti or anti. Okay, you can draw the other type of conformation. Those will have higher energy, means less stable than this anti conformation of Newman. So now how to understand the real structure or perspective structure of this Newman? So you can look that Newman from right side. If you look from right, you will see two carbons, this carbon and the other carbon. Okay, that's this carbon is this front carbon. The big circle behind the carbon behind it is this carbon. You will see this methyl as left, point to left. Okay, and you will see the bromine point left but toward to you. This methyl is point left but is in a plane. The hydrogen is out of plane, is point away from you. If you look from right, this hydrogen is away from you. Now look at the other carbon, this carbon. You will see the hydroxyl group is pointed to you, also tilt right to the right, and hydrogen is away from you. That is this hydrogen, and this methyl will be down but pointed to right. So that will be the perspective, we'll say translated or of this Newman projection. Normally we will not show the hydrogen in the skeletal structure, and also we will rotate this a little bit, make zigzag of this backbone of the 4 carbons. Okay, so the backbone is butane, and then we just need to show the bromo group and hydroxyl group. So this is the 3-bromo 2-butanol. That's the normal perspective structure of this Newman projection. Okay, another type of 3D structure is called Fischer projection. Fischer projection looks like this is a 2D because you don't see wedge and dash, and so just a line. But the real meaning of the Fischer is a perspective. So all the vertical bound are away from you, and all the horizontal bound are pointed to you. So those are out of plane. So this is the real 3D structure of this Fischer. Okay, this is the 3-chloro 2-butamine, and this is also not normal perspective structure. So if you want to draw the normal, you can look at from right again. Now if you look from right, you will see this perspective structure. So since this methyl is pointed away from you, from this right side it will be pointed to right. Same thing, this methyl will point to right. This amino group will point to you. This hydrogen will be pointed away from you. Chlorine will point to you, and hydrogen point away from you. So that will be the perspective from right view. And then you can rotate this to 90 degree. Basically, you will have this perspective. Normally, you want to draw the carbon chain as zigzag, so that will be more stable. So you can rotate this single bond 180 degree. So then this methyl will be rotated to down from top to down, and then this hydrogen will be rotated. This hydrogen was away from you, now will be point to you because you rotate 180 degree. This chlorine will be rotated to away from you. So that will be more stable structure, and then you can get rid of the hydrogen because normally the skeletal structure you don't need to show the hydrogen. So now zigzag, again I rotate a little bit. So this is the 4-carbon backbone, the butane, and this is the amino group here, and this is the chloro group over there. So this is the 3-chloro 2-butanamine. Okay, that's the Fischer projection. How to convert the Newman projection to Fischer projection? I'll give you an example here. Okay, so this is again the anti-conformation here. So this is the 2-bromo 3-chlorobutane. Okay, so to convert that to the Fischer, you need first rotate the methyl group to here. So rotate this methyl group to here to be same position of this methyl, basically eclipsed conformation. When you rotate this methyl to here, the hydrogen here, this hydrogen must be rotated to here, and the chlorine must be rotated to here. Okay, so that 180-degree rotation will make this eclipsed Newman projection. Although this is much less stable because you have a lot of steric hindrance between these two methyl group. But this is a way to draw the Fischer, okay? Because you want to make sure these two methyl group are all away from you. And then you look at that from top, you will find these two bond away from you. These two methyl group are away from you. So from top view, you will see this methyl is this methyl behind, so the carbon on the behind carbon, and the methyl on this front carbon will be this methyl if you look at it from top. And then this hydrogen will be this hydrogen. This bromine on the behind carbon will be point to you. See, from top. And now this hydrogen is this hydrogen, and this chlorine will also be pointed to you. So this will be the perspective if you look at that at this eclipsed Newman projection. And to change it to normal Fischer, so because normally Fischer you just need to draw the line, you don't need to show the wedge and dash, because that means it's a point away from you, that's away from you, that's a point to you, point to you, point to you, point to you. So this is the definition. So you just need to draw this Fischer. That's normal Fischer projection of this Newman. Okay. Now let's look at how. Okay, now how to convert a Fischer projection to Newman projection. I use this compound. This is the alcohol as an example. So you look at this as the Fischer projection. Now, if you want to draw the Newman, you need to first draw the perspective based on the definition of Fischer. The vertical bond, they are all away from you, and the horizontal bond are all point to you. So you just draw the wedge and the dash. Now, if you look from bottom, you will see this carbon as the front carbon, this carbon will be the behind carbon. So, and then this methyl group will be down, and then this fluorine will be up, and hydrogen will be up. That's the three attachment on this carbon in front. And then the carbon behind is that big circle, and you will see hydrogen up, hydroxyl group up, that's this hydrogen, hydroxyl group, and the methyl down. Now, this is the Newman now, but this is not very stable Newman because you have a two methyl group have too much steric hindrance here. So you want rotate this methyl from here, from the eclipsed to anti. And then when you rotate 180 degree, that will be anti, and this hydrogen will rotate to here. Fluorine will rotate to here. So that give you most stable Newman projection. That is anti. These two methyl group are opposite. Okay, so this is how you draw the different 3D structure, include the perspective, Fischer, Newman. And if you have any questions, please let me know. Okay, good luck.